Good morning, dear friends. Myself, Dr. Chandrakant Shivajahir, Assistant Professor in Chemistry, MGVs, MG College, Malegaon Camp, Malegaon, Nasik. So, dear FYBS student, in last lecture we complete chapter first, that is chemical energetics. So, in second chapter, now we start for second chapter, that is chemical equilibrium. So, what is chemical equilibrium? Processes under this equilibrium condition for chemical reaction at equilibrium, we see all in details in this second chapter. So in introduction, last chapter we consider this concept of entropy, first law, second law and third law of thermodynamics. So here in introduction we consider this second law of thermodynamics is based on spontaneity process. Spontaneity is increase of entropy, so delta S value greater than 0. So in second law, this thermodynamical condition is spontaneity, which is based on entropy function. And for the spontaneous process, this condition is thermodynamical condition is delta S is greater than 0, where delta S is a entropy change applied to the isolated system. So we also know this different type of systems in first chapter. But in order to decide about the feasibility of process, this reaction occurs or which extent, for that we must know the total entropy change. This entropy you consider for the system, isolated system, only system. But in order to feasibility of process, we must require the total entropy. What is total entropy? This entropy change system, in the system plus or as well as in the surrounding of that system. So system plus surrounding, both changes we consider in feasibility of process. Generally this chemist, like we are the chemist, so we are interested in the system which interact with the surrounding environment than the isolated system. So when we do any reaction in practical, at that time this effect of surrounding is takes place on the system. Our chemical reactions are not isolated. We consider this reaction in presence of surrounding, and so it could be preferential to have a criteria. So in this case, these chemists do not bother about the surrounding changes. So in preferential to have the criteria, they applied to the system without considering the change in surrounding. So these chemists, we people, do the reaction, do the process, or we carried out this feasibility of process without considering or without worries about the surrounding. For example, for that we required certain criteria for that processes. For example, this phase change chemical reaction that occur at constant temperature, constant pressure. So this criteria we apply. So here this entropy which depends upon only isolated systems. So entropy is not a sufficient condition for the chemist to carry out such type of reactions, chemical processes, and thus we have to need, and hence a new thermodynamical function, the energy, free energy or Gibbs energy is introduced, and it is defined as G. This free energy, Gibbs free energy G, is defined as or is equal to H minus Ts, where H is a enthalpy, T is a temperature, and we know S is entropy. It is a state function, and this G is also a state function. Hence we use, so forever in this second chapter for our chemical teaching, we consider this change in Gibbs free energy. We don't consider this G singly, we consider this change in Gibbs free energy for a system which occur at constant temperature and pressure, and thus this definition, this equation become delta G. So in our teaching we consider delta G, change in Gibbs free energy, which is equal to change in enthalpy minus T, change in entropy. This T, just now we say this constant temperature and pressure. Temperature is a constant, it is not change, it remain constant, and hence the criteria for spontaneity of process now become delta G less than 0. So previous criteria spontaneity is entropy change is positive greater than 0, entropy change is greater than 0, When we consider this increase in entropy change, this entropy change present in a negative fractions. When entropy change increases, this difference delta H minus T delta S goes on decreasing. This value of delta G goes on decreasing. When delta S increases, delta G decreases. More the entropy change, process become spontaneous. At that time, delta G value goes on decreasing. And hence, criteria for spontaneity of process is delta G is less than 0. Delta G must be negative for spontaneity of process. Here, this delta S entropy is positive, but delta G is negative for spontaneity of process, where this negative factor is more, that is increase of entropy. So we introduce this Gibbs free energy change in chemical reaction. Just now we see this thermodynamical function, this spontaneity of any reaction. This Gibbs free energy is a new thermodynamical function we introduce, that is delta G. Now we consider change in Gibbs free energy in whole chapter, also called as a reaction free energy. This delta G is also called as a reaction free energy. This equation is defined as a difference in molar Gibbs free energies. At that time, this G become Gm of the product and the reactant. M is a molar Gibbs free energy. Consider this reaction: A plus B gives C plus D. A of A mole, B of B mole, C produce C of C mole and D of D moles. So this delta G change in Gibbs free energy for this reaction is a Gibbs free energy of product, that is C G Gibbs free energy of C into moles of C, Gibbs free energy of D into moles of D, plus, so these two are the products, minus Gibbs free energy of A into A mole, Gibbs free energy of B reactant into B mole. So this product minus reactant. So in this case, this delta G is a total Gibbs energy of product minus total Gibbs energy of reactant, and thus we write this equation: delta G is equal to summation of this NP Gm of product minus summation of NR Gm into reactant. This Gm is a molar Gibbs free energy multiplied by the number of moles of product, molar Gibbs free energy multiplied by the N number of moles of reactant. So this NP and R are the moles of product and moles of reactant. Now we consider this standard Gibbs free energy. Just now we define molar Gibbs free energy. Now we consider standard Gibbs free energy, that is delta G. We write this node. This node indicate standard condition. We call it the degree or node. This small 0 indicate standard condition, and it is defined as the standard Gibbs free energy is defined as Gibbs free energy of reaction in terms of standard molar Gibbs free energy of reactant and the products. So this equation now we shift to the standard condition. That is the only change. So instead of molar condition, we use the standard conditions for each product as well as the reactant, and thus the standard molar Gibbs free energy is the difference in Gibbs free energy between the product in their standard state and the pure reactant in their standard state at 1 bar. This 1 bar is the pressure at a specified temperature. So this is a standard condition. This meaning of degree or this small 0 is the standard condition. When we consider pure element, most stable form of element, at that time it shows the lowest Gibbs free energy. If one of the element is the pure form, this reactant is in pure form, at that time his Gibbs free energy is very low, lowest. In other words, the standard molar Gibbs free energy of reaction is the change in free energy that will occur if reactant in their standard state are converted to product in their standard state. That is the condition. Condition is a standard condition, and we just define the standard condition in terms of pressure and temperature. So continue with this. If it is fixed quantity for a given reaction and does not vary in the reaction process, so particular amount of reactant combine to form product and there is no change in reactant or product, at that time these quantities are fixed. At that time we again change that previous equation. So instead of, see the previous equation, so this is our molar Gibbs free energy equation. Now we applied standard condition in molar state. Now we change this molar state when the fixed quantity of reactants and product are present. At that time we write this small f. So this small f, so it is also delta G0 of f, or this delta G0 is a standard Gibbs free energy of formation. This delta Gf is a standard Gibbs free energy of formation, standard, and Gibbs free energy of F is formation. That is the change in free energy that accompanies the formation of 1 mole of the substance from its constituent element. So this constituent element reactants are converted into substance. The formation of 1 mole of substance from its constituent element when substance and elements are in their standard state. So this is a formation reaction where quantities are fixed, not change, and thus with this standard Gibbs free energy of formation we define as a like this. The standard free energy of formation of an element in the standard state is 0. Standard free energy, this delta F of not in standard condition, delta F of standard condition of any element in its stable form. In its stable form, the standard free energy of formation of element in its standard state is 0. When the standard condition is applied to the element, then this entropy is 0. In previous chapter we consider this when standard condition applied to the element, at that time we consider this delta H is 0. So here is delta G is 0. The values of delta G0, that is a change in Gibbs free energy at standard condition or standard Gibbs free energy change, tells nothing about the rate of reaction. It implies at equilibrium position. So in introduction we see this is a state function. So it gives the only reactant and product changes. So we don't have the idea about this rate of reaction or intermediate processes. When we calculate this standard molar Gibbs free energy, so we have the standard enthalpy, we require the standard enthalpy and standard entropy data, and these data are provided in problems or example solving. At that time these data are given in tabular form. By using this data we solve these examples for calculation of standard molar Gibbs free energy change for that particular reaction. At that time we consider all these element in standard state Gibbs free energy is 0. We apply this equation for problem solving. So here the change in standard Gibbs free energy change is equal to standard enthalpy change of formation. Standard Gibbs free energy change of formation is equal to standard enthalpy change of formation minus T is constant. Just now we say temperature, pressures are constant. Standard entropy change for the formation reaction, and for the reaction carried out at constant temperature, T remain constant, other factors are changes. So this equation is very important for problem solving. Datas are given, we put these values in enthalpy change, entropy change, and we solve these equations. So we consider that in problem solving part. Now new terms, exergonic and endergonic reaction. So we know endothermic reactions, exothermic reactions. At that time what we consider H, enthalpy change, delta H, if the enthalpy change positive, negative. Here this exergonic, endergonic terms depends upon the entropy, it is a free energy change, standard molar free energy change for that reaction. So what is exergonic reaction? Reaction that have a negative value of this delta G0, where energy is released, are called as a exergonic reaction. Why energy is released? So we calculate this value by summation of Gibbs free energy of product minus summation of Gibbs free energy of reactant as standard condition. When product is stable, Gibbs free energy is a product minus Gibbs free energy of reactant, and this difference is negative. At that time it is called as a exergonic reaction. For example, formation of water from its element. We know hydrogen gas combined with oxygen to form a water. Second, reaction for formation of carbon dioxide from its element. So carbon combined with oxygen to form carbon dioxide. These compounds are thermodynamically stable, very important. Water and carbon dioxide are thermodynamically stable compound, and this reaction is spontaneous reaction. We talk and with respect to the element, with respect to their element, that is hydrogen, oxygen, carbon, oxygen. These products are stable, and thus this product formation is a spontaneous process, and thus the delta G value is negative. In introduction we say at the bottom, this new condition for spontaneity of process is delta G is negative, and this spontaneous process occur to the formation of stable product. Second reaction, endergonic reaction. Reaction that have a positive delta G, 0. This standard molar enthalpy change is positive, where energy is absorbed, are called as a endergonic reaction. Example, formation of diamond from graphite. Graphite is converted into diamond. Graphite is one form of the carbon, is converted into diamond. Diamond is very valuable product, glass like valuable product, and at that time this standard molar entropy in free energy change or Gibbs free energy change is equal to plus 2.9 kilojoule per mole. It is positive. This delta G0 is positive, that is called as a endergonic reaction. So opposite to this, in this case this compound are thermodynamically unstable. Diamond is unstable as compared to graphite. Graphite is stable as compared to diamond. So this reactant graphite is stable as compared to diamond, that is a product with respect to their element. And this compound cannot be, see, these compounds are thermodynamically unstable with respect to their element or reactants. So this element graphite is stable, diamond is unstable. So for formation of such type of unstable compound, this compound cannot be formed directly like this. Spontaneous reaction is not occur. This compound cannot be formed directly from its element. This compound must be synthesized by alternative route. So it is not simple spontaneous process. We apply different parameters, pressures, condition, and then these unstable compounds are synthesized. So this is the for example. This is the example we consider. We have many reaction. In that case, we applied different conditions for formation of product, and we called it as a synthesis of that compound. So this much part we consider in this lecture. Remaining part we see in next lecture. So best of luck. Keep on study all the material regularly, daily. We take exam on a first chapter anytime. Thank you.